In this lecture, we will be dealing with our second treatment of derivatives of trigonometric functions. So last time, remember, we had seen that the derivative with respect to x of sine of x is cosine of x, and the derivative with respect to x of cosine of x is minus sine of x. We now look at the other trig functions: tangent, cotangent, secant, and cosecant. Now these are different than the sines and the sine and the cosine function in that their domains are not the whole. The domain is not the whole real line. Remember, for these functions we have asymptotes. We have problems because of zeros in the denominator. So for instance, remember that tangent of x is sine of x over cosine of x. And so we saw that tangent had an asymptote, vertical asymptote, for all the x at which cosine of x is 0. We have a similar issue with secant of x, which is 1 over cosine of x. Same issue, has a vertical asymptote whenever cosine of x is 0. That being said, for any x where the function is defined, each of these other four trig functions are differentiable at such x, and we have these rules for their derivatives. So the derivative with respect to x of tangent of x is secant squared x. The derivative with respect to cotangent of x is minus cosecant squared x. The derivative with respect to x of secant x is secant of x times tangent of x. And the derivative with respect to x of cosecant x is negative cosecant x, cotangent x. Now you might have wondered in the past, why are the trig functions named the way they are? Why is secant 1 over cosine instead of 1 over sine? Why is tangent sine over cosine instead of cosine over sine? Well, the answer comes from this layout of derivatives. And let's actually rewrite our sine and cosine. So the derivative with respect to x of sine of x is cosine of x, and the derivative with respect to x of sine of x is derivative with respect to x of cosine of x is minus sine of x. And you can see here the pattern. If the trig function has a co at the beginning, its derivative has a minus sign. If there is no co, no co at the beginning of the name of the trig function, there is no minus sign in front of its derivative. So this shows you why the trig functions were chosen, why tangent of x is sine over cosine rather than cosine over sine. But this is a very helpful rule to remember the derivative of the trig functions, because this means, say, the derivative of tangent of x, that's secant squared. If you remember that, then to get the derivative of cotangent of x, you just do cosecant squared instead of secant with a minus sign. And the same sort of thing goes for the derivative of cosecant. Instead of secant tan, you have minus because of the co, and then cosecant cotan. So this is another helpful, it's always helpful to have these tricks to be able to memorize as little as possible. Now, how do we actually derive these? And we will do one of them. We'll derive this formula for the derivative of secant of x. And it's actually quite straightforward once we recognize that if we just rewrite secant of x as 1 over cosine of x, we can use our regular differentiation rules for this. So the derivative with respect to x of secant x is the derivative with respect to x of 1 over cosine of x, or cosine of x to the minus 1. And we've learned this is a chain rule problem. So for chain rule, we do the derivative of the outer function. So we do power rule, minus 1, leave the inner function alone. cosine of x, reduce the exponent by 1, and then multiply by the derivative of the inside, the derivative of cosine, which is minus sine. If we simplify this, we have a minus minus, so those two will become a 1, and this results in sine of x over cosine squared x, which is then rewritten as sine of x over cosine of x times 1 over cosine of x, which is tangent of x times secant of x, which is what we wanted. So with this in mind, it's also true that if you run into a problem, you're working on an exam question or something, and you forget one of these derivatives, then you can just write what secant is, or tangent, or cotangent, in terms of sines and cosines, and use our differentiation rules to obtain the derivative. And again, this is how any of these 4 derivatives listed in this theorem are derived. So, let's see this in action. Let's do this example. So suppose we have cosecant of root x. Well, first of all, this is always easier if we rewrite the roots in terms of powers. So this is cosecant of x to the 1/2. Now, we use our previous theorem. Remember, we saw that, say, cosecant of u was equal to negative cosecant u times cotangent u. This was the previous theorem, just writing things in terms of u, since we have a chain rule problem here. This would be a case where our u is x to the 1/2. So what we have, when we use our chain rule, we do the derivative of the outer function, leaving the inner function alone. So we have cosecant, negative cosecant, u times cotangent of u, times the derivative of the inside, we can write it this way, du dx, we substitute in for u, this is negative cosecant root x times cotangent root x, and du dx, we do power rule, 1/2 x to the minus 1/2. Or cleaning this up, negative cosecant root x times cotangent root x, all divided by 2 root x. I did this out with the chain rule written explicitly, naming the inner function u, and then dealing with the outer function. You don't necessarily have to do that when you do this type of question. You can go from this step here directly to this step here. But sometimes it can be helpful to see, to remind us of exactly what we're doing when we use chain rule in this way. Okay, let's look at another example, a more complicated example. So we have y is the cube root of cosine of tangent. Again, it's always easier to eliminate the root expressions and write things in terms of exponents. So we have this cosine of tangent of x raised to the 1/3. So, chain rule, a couple times actually. Our first outer function is something raised to the 1/3. So our derivative, we do power rule on the outer function, leaving the inner function alone, cosine of tangent of x. Now reduce the power of the exponent by 1, so 1/3 minus 3/3. is negative 2/3 times, and let's just black box it for the moment, the derivative with respect to x of what's inside. This term we can focus on separately. We do chain rule again. So the derivative of the outer function, leaving the inner function alone. The derivative of cosine will be minus sine. So we have minus sine of tan x, so leaving the inner part alone, times the derivative of the inner part, and the derivative of tangent of x with respect to x is secant squared x. So this gives us, if we clean this up a bit, we can bring this term raised to the minus 2/3 to the denominator, where it'll have a positive 2/3 power. And this term in purple will be our numerator. So we have negative sine of tangent of x times secant squared x, all divided by 3 times the quantity cosine of tangent of x raised to the 2/3. So this would be a more challenging example because we're including the use of chain rule. Okay, let's do another one. And this is a classic example. You hear it a lot in math up to this point, that really you should be using radians instead of degrees. And it's very common that people tell you that, but don't necessarily justify it. So let's actually see why that's the case. And let's calculate just the derivative of sine of x if x is in degrees rather than radians. Well, the issue is, in order to differentiate, and again, I should be explicit, this is the degree sign. This is not a 0 power. So if we want the derivative with respect to x of sine of x, where x is in degrees, the first thing we have to do is change from degrees to radians. And to do that, we multiply the degrees by pi radians over 180. And now x is in radians. Well, if we take the derivative of this, we have a chain rule problem. Derivative of the outer function, derivative of sine of something is cosine. Leave the inside alone. Times the derivative of what's inside, which is just pi over 180. And if you want to go back to degrees, we just reverse this. This is of course still, if we want to switch to x degrees, we multiply this by 180 over pi. And we get an answer of pi over 180 times cosine of x degrees. So this is the key. If you're working in degrees, the derivative with respect to x of sine of x degrees is pi over 180 times cosine of x degrees. So the result for differentiating sine or cosine when you have your angle measured in degrees spawns this pi over 180 constant. When you work in radians, the derivative of sine of x is just cosine of x. So this is one of the main reasons why you want to work in radians rather than in degrees. Let's do another example. One more. suppose that we have y equals x squared times tangent, or why don't we do cotangent of x cubed, and we want dy dx. In this case, we have product rule. So the first times the derivative of the second, and remember, the derivative of cotangent u with respect to u was, and again, the way to remember this is the derivative of tangent is secant squared. The derivative of cotangent is minus cosecant squared of u. So, back here to our product rule. First, x squared times the derivative of the second, and so we have a chain rule problem. Derivative of the outer function minus cosecant squared, leaving the inside alone, of x cubed. Times the derivative of the inner function, which is 3x squared. So there's our first term from using product rule. Then we do the second, cotangent of x cubed times the derivative of the first, which is 2x. And we could simplify a bit. We have a minus 3. We have x squared times x squared, so x to the fourth, cosecant squared of x cubed, plus 2x times cotangent of x cubed. Let's look at an applied example, and we will delve into these kinds of questions much more when we get into the section on implicit differentiation and related rates. But here we have a physics problem. So we want to draw the picture and understand what's going on. So a balloon is rising vertically. It's being observed from a point on the ground. So we have our balloon. We have the ground. "300 feet from the spot." Well, it's being observed 300 feet from the spot directly beneath the bottom. So there's somebody standing 300 feet away, watching this balloon. And then we're told, we have a question about what rate it's rising when the angle between the ground and the observer's line of sight. So we should draw the observer's line of sight. And we're told something about this angle here. So we're asked a question, at what rate is the balloon rising when the angle is 45 degrees and we have a rate that the angle is increasing? So the first thing we need to do in a question like this is set up a mathematical model. So we need to think about variables. Well, first, we need a variable for the height of the balloon. So the balloon is moving, and that's moving up, so it's probably a good idea to call the height just y with our usual calculus conventions. We have an angle, we could call that theta. And let's think about now with these variables, if we have enough to model the situation, model the scenario. And notice we have a triangle here. So we can relate y and theta. Specifically, before we even start fitting things, we can relate y and theta by our SOHCAHTOA rule. We know the tangent of theta is opposite over adjacent. So we know that tan theta is y over 300, or y is 300 times tangent of theta. So with these variables, we already have a setup that relates them through this equation. Okay, so what rate is the balloon rising? Well, that is saying what rate is the balloon's height changing in time. So the rate at which the balloon is rising will be the derivative of y with respect to t. So we're asked to find what that rate of change is given a specific instance. And that instance is when this angle is 45 degrees and the angle is increasing at 1 degree per second. If the angle, theta, is changing in time, that gives us a derivative of theta with respect to time. And we're told our instant, well, yeah, we have 1 degree per second. So what we now have are these two rates, dy dt, d theta dt. But then we also have a relationship between y and theta. So what we want to think about is our change rule, our chain rule. So our chain rule is that dy dt is, and theta is our intermediate variable. So t is our independent variable, theta is our intermediate variable, and y is our dependent variable. So dy dt is dy d theta times d theta dt. dy d theta we can get from here. So because y is 300 tan theta, we know dy d theta is 300, the derivative of tangent of theta with respect to theta is secant squared theta. So our dy dt becomes, we can substitute that in, 300 times secant squared theta times d theta dt. So we now want to think about the question that we have to answer. What is dy dt at this particular instance? In the particular instant, and you can think about this observer as watching the balloon go up. So this blue line of sight is getting steeper and steeper in time until just that one moment where this angle between the ground and the line of sight is exactly 45 degrees, or pi over 4. And we're also told at that instant d theta dt is increasing at a rate, an instantaneous rate, of 1 degree per second. So we want to use that information here. So let's come back. Let's summarize things. We just said dy dt was 300 secant squared theta times d theta dt. That was the big result that we put together with our mathematical model. And again, we're told d theta dt is 1 degree per second. And at that moment, theta is 45 degrees. So what we want to do now is get things in terms of radians. So, in radians, 45 degrees is pi over 4. Our rate of change of 1 degree per second, right, so we'll say here we're changing to radians. d theta dt in radians, we need to multiply that 1 degree by pi radians over 180. And so we get pi over 180. So plugging in these two pieces of information to our formula for dy dt, we have our theta in radians, and then we have our d theta dt. So dy dt becomes 300 times secant squared of pi over 4 times pi over 180. And we need only simplify this. With secants, it's usually easier to rewrite it as cosine. So secant squared would be 1 over cosine squared of pi over 4. (300 over 180), that's 30 over 18. Or 10 over 6. So this is 10 over 6 pi. Cosine of pi over 4, right, remember what that is. That's shorthand for cosine pi over 4 squared. 10 over 6 is, of course, 5 over 3. So 5 pi over 3. Cosine of pi over 4, we know from our pi over 4, pi over 4, pi over 2 triangle, is root 2 over 2. So this is 5 pi over 3 times 1 over. So root 2 times root 2 is 2. And the denominator, 2 times 2 is 4. Or 5 pi over 3 times 2, or 10 pi over 3. So this is the rate at which the balloon is rising in feet per second at that instant where the observer's line of sight makes a 45-degree angle with the ground. We will see these types of problems in more detail, but it's important to get used to them because they are really a fundamental type of problem that we deal with in calculus.